might be at least important for today. So just to kind of give you an idea of where we're at, we're in week 11 of the course, so things are beginning to wrap up for us. We're definitely on the tail end, and we're finishing up, the story of how statistical inference is supposed to work. So this week, you'll have another reading assignment this week. It's a whole lot like the last few reading assignments, which are sort of summaries. The real goal, I think, of those reading assignments will be to do the reading and then think a little bit about what's on the assignment, formulate some questions, and submit them. I guess the last few weeks will go back to a system of reading assignments, which you're really having to answer questions. We'll be past the point where these sort of summaries are, I think, necessary. So to that end, I think reading assignment for chapter 18 is due this Friday. That's not any different. So you can find that in the week 11 course module on the left-hand navigation. In addition to that, there's a written assignment 7, which is related to what we're talking about this week, and that's due as it normally is next week at 5 p.m. next Tuesday. There's a homework 10, which is also assigned and due next Monday at 5 p.m. And so I need to, write up the overview for the week, but that's basically where things stand. So I don't really anticipate any major changes for this week. Next week will be similar to this week. There'll be a homework, a written assignment, a reading assignment for week 12 as well. For week 13, I think I'm going to not have the written assignment. I was sort of debating this, but I think 8's probably enough for the written assignment. But other than that, things will be the same into week 14, other than the written assignment being due in week 14. The class proper, I think, if I've timed it right, the new material that we'll cover in some time in week 13. We'll use week 14 to do some optional items or talk about the course, sort of giving kind of a bird's eye view of the experience in week 14, depending on how people feel about things at that point in time. And then the finals the week after that. So that's kind of where we're at right now. Not a whole lot of distance to go. You just finished the second exam last week. I don't really have any comments about it. It seems like it went fine. The scores on the second exam were a bit like the scores on the first exam. So things are okay. I think people are contributing. They're doing well. I don't have any complaints about what people are doing so far. So as the course begins to finish up, keep doing what you're doing. On Blackboard, I believe the grades are weighted according to the syllabus. I always need to go back and double check, but I seem to remember doing that before the semester started. So you can kind of get an updated version of where your percentage grade stands right now out of 100. Always go back and review, make sure you believe everything's accounted for. In particular, if you get a 0 or something like that on an assignment, what most likely has happened is that you submitted a blank document. This is almost certainly a mistake. So if something like that happened, let me know. So go back and check. And I think right now that's about all I have to say of an administrative nature. One more thing. A couple of people reported issues with my stat lab, in particular with doing homework that's due later today. Yeah, so Walker asked the question, when will it happen? I think I probably have to refresh it. So I think there's usually a button I push on Blackboard in order to make sure that the grades migrate over and are accounted for in the new calculation. It does this automatically, I think, for the most part, but I haven't seen or I haven't checked manually to see if those grades are there yet. So okay, I mean, if they're already there, then they're accounted for. So sometimes it accounts for things like if you took the exam on Friday. I mean, I guess it depends, but I haven't checked. It's weighted properly. And usually from time to time I go back and I sort of manually refresh so that I'm confident that, the grades are really in there as I sort of expect them to be. But again, check to see that they're there. And as always, I mean, if you have the syllabus, you can make sure that this percentage grade that you're getting sort of corresponds to what you expect to get. Right, but one more thing about my stat lab today. A couple of people have reported that there appear to be issues with doing the homework or getting access to it. I think someone reported that on Sunday, and there was some kind of, what I understand is that there's some sort of software update, which always creates problems with this type of software. So what usually happens after a software update is that something somewhere else breaks. There's some issue, and I think that's probably what's happened. Check later today if you can get access to it. I think I tried to get access to it a moment ago, and I could get into the site, but I couldn't see anything. And I guess that means that things are slowed down to the point where I can't access it. if you can't access it, then I don't really see, if, I'm not going to really require that homework. I guess it's 9, it's due at 5 if people are trying to complete it this afternoon. So what I imagine I'll do is I'll probably just sort of delay the due date for a couple of days to give us enough cushion to ensure that the service is returned and people have time to sort of consider the assignment. So, it's no big deal. If there's some sort of delayed interruption, then maybe that's an issue. But I guess we can just sort of be thankful that it didn't happen last week when you were taking the exam. So if you have trouble accessing it, you might. That's not surprising. I think a fair number of people are. I got a report from an instructor who was also having trouble with access. So it's not unexpected. So don't worry about it. I'll just delay the assignment. No. So Natalie asks, is there no written assignment due this week? There'll be a reading assignment due this Friday. There's no written assignment due this week. If there were, it would have been assigned last week. So the written assignment 6, I guess you had due last week, but I didn't assign anything during the week of the exam. There's a written assignment 7, which will be due the following week. And there will be a written assignment 8 that I will assign next week that will be due in week 13. And I believe that should be the last one. I could sort of shoehorn a 9th written assignment in there, but to be honest, I tend not to want to have a lot due that last week if people are beginning to point in the direction of the final exam. So I kind of want to have a laid back, I guess, week 14. So there should be a written assignment 7 up there now. It concerns what we're going to be talking about this week. It should be due in week 12. There should be a written assignment 8, which I will publish probably later today or tomorrow, that will be due in week 13. And I think that's probably enough. I could barely get in week, a 9th one, but it may not be necessary at this point, to be honest. Does that make sense? Yes, Lily.
I have an exam question and kind of just like, I don't know if this is up for discussion or anything, but I know that the whole concept of the questions disappearing once you do them and you're not able to go back and check them kind of threw me through a loop. Just because there was one question where I clicked the wrong one and accidentally submitted it and couldn't go back. So will that be the kind of the same, will that be the same way for the final, or is that kind of up for debate? I don't know.
It can be up for debate if people would want another format. I mean, I'm actually indifferent to which format gets used. To be honest, the reason why that format I think is reasonable is that it's sort of a hedge against people, pausing for too long and looking up questions on the internet or something like that. So I mean, that's why it's there, but there are other options that are available, and I'm not wedded to any particular set of choices.
Cool. All right. Thank you.
So, so in any case, anyone have any other questions they'd like to ask at this point?
If your exam is not in yet, what should you do?
Don't worry about it. So if you took the exam, there's a record of it. So I can always go back and look at what the grade is. And sometimes with Blackboard and the interface with my stat lab, I have to go back and manually, there's certain buttons I can push within Blackboard, which will cause the grades to migrate from my stat lab to Blackboard. So it's not a big deal if it isn't present there right now. It's just an issue where for whatever reason hasn't reported. And if I had to guess, it's probably related to the software update that they conducted this weekend. If I go in there now and mess with it, I'd be afraid that nothing would happen, because I think the system actually is down right now or is experiencing some sort of reduced form of functionality. But if you know your grade, it's safe to assume that at some point, in the next couple of days, the grade will report. Does that make sense? All right, so any other questions that people might have? All right, so I'd like to talk a little about some old material, kind of get into the new material this week. Like I said earlier, I'm pretty comfortable with how people are treating the material. They seem to be treating it seriously. Things seem to be going, in a positive direction in the course. So keep doing what you're doing. I want to kind of give a brief summary of what we're doing, of what we've done so far over the last couple of weeks, just to sort of keep people focused on like the key tool, and then give you a summary, at least from a certain point of view, of what we're going to be doing this week. Then maybe have groups work on a couple of examples toward the end. So let's see. Let's just start with a brief summary, just sort of a general description of where we're at in the course. So just a reminder, over the past, I guess it's 3 weeks, we've discussed estimation, inference. And the two examples we've considered is we've talked about discussed the population proportion P and the population mean mu. And we've gotten very similar types of answers depending on context, but they've not been that different. To estimate P, we use P hat, which is the sample proportion, and to estimate the population mean mu, we consider the sample mean x bar. So again, it's difficult because I think we're sort of at the part of the course where there's quite a bit of terminology to kind of to try to process. When you see something like P hat, you're thinking about an estimator, a statistic, lots of names for it. Same thing's true for x bar. When you're thinking about things like P or mu, you're thinking about actual numbers, though you don't know what they are. Now, to our telling, to our way of thinking, P hat and x bar are random variables, and they're equipped with a probability distribution because of that fact. So under conditions, to sort of term these reasonable, we're basically saying under reasonable conditions, the central limit theorem is basically saying something like this. The distribution for P hat is normal with expected value, the thing we're trying to estimate, and standard deviation equal to that square root that we talked about. So you get something that looks a bit like this. So n is the sample size as always in cases like this. It guarantees that. And in addition to that, the theorem that we're talking about guarantees, that x bar's distribution is similar. So like we've said before, again, remember that n is some sort of fixed sample size. Here in this telling, sigma represents the standard deviation of the population. And so our estimates, our formulas for the estimates, for the interval estimates that we want for the parameters, the unknown parameters, as a result, tend to look a bit like this. So for P, an interval estimate might look something like, so let me, this sort of shoving a little under the rug here, but our interval estimate might have some sort of generic formula, which basically has this appearance. And for mu, the general formula we have, people might remember this T statistic. Oops. We have something that looks like this. And in some in some general sense, when you're talking about anything that has this appearance or maybe this appearance, there's this idea of the margin of error. And if you're doing an estimate, which depends, and you're talking about, say, a confidence level, the confidence level and the margin of error correspond through either Z star or Tn minus 1 star. So the confidence level corresponds to a choice of either C star or Tn minus 1 star. And again, the intuition that you might have is that the higher the confidence level, the larger Z star or Tn minus 1 star should be. And in some sort of extreme case, if you're talking about something weird like a 100% confidence interval or a 100% family of intervals, you're basically just talking about a bunch of real lines. Basically, your interval would have to be infinitely wide in order to get that degree of confidence. So of course, you almost never talk about that. And you almost never talk about a 0% confidence interval either, right? Because that would entail basically just having a point estimate. So are people with me so far? Like, this is the state of the conversation. We have some unknown parameters. I'm about to do an example that we've talked a little about. And then I'd like to reformulate that example in the language that we want to use this week when we reformulate inference in an equivalent way, but maybe it's not so obviously equivalent. So do people kind of understand? Yes, Abby.
Could you go over quickly what T star n minus 1, like how you would find that?
Absolutely.
Thank you.
Yeah. So for something like, so both T and, so I guess I should write, so Tn minus 1 star, it's called a critical number, critical value, something like that. And you need it in this system of estimations because most often we don't know the population standard deviation. So if you knew population standard deviation, you could treat this as, say, you could treat this in exactly the same way that we were treating proportions. You could use, say, the standard normal curve to come up with the value of you can come up with a critical number. So to find, just to take an example, let's say that we're discussing a 99% confidence interval estimate. Now, when you talk about this confidence level, you have to, in your mind, sort of perform some abstraction. You're not really thinking about one interval, but you're thinking about some sort of general formula which will generate a family of intervals which has 99% as a coverage probability, or maybe more simply, if you think about all the intervals that you could possibly construct, 99% of them will contain the parameter and 1% won't. And so there's some reasoning which allows you to convince yourself that this concept makes sense, but that reasoning sort of depends on knowing something about the sampling distribution of things like X bar. So if you don't know this, we're stuck. We're thinking about the so-called standardized means. And so if, let's say further, that the sample size, just for the sake of the example, let's say our sample size is like 24 or something like that. And so to find, so I guess I should say we're looking for, so using this formalism, we're looking for T star. So when you write n minus 1, n represents the sample size. So if the sample size is 24, we're looking for Tn star sub 23 in the language of the example. So when we're trying to come up with that, you would go to, the easiest way of coming up with it is just go to StatCrunch. Hopefully it loads. So to find that, go to Stat, Calculators, T. And the T, or the family of T distributions, is somehow brought up. Now, when you're talking about 23, the number 23 in this example the role that it plays is it's the number of degrees of freedom. So change the 10 in this case to 23. I also need to go in between because I want sort of these cutoffs, this range. And so to find what the critical number is, I'm in this situation, I simply enter 0.99 for a 99% confidence interval. And what I'm looking at is essentially 1% of the area in the tails, or equivalently 99% in between. So what that's telling me in this case is with a sample size of 24, I'm expecting my critical number associated to the 99% family to be about 2.80, 2.81, it looks like. So I would write T sub 23 star in this case, it's about 2.81. So, before I go on, does that make sense? That's how you do it. So the degrees of freedom that you're talking about corresponds to the sample size. It's one less than that. And you're using the family of T distributions because the fact that you don't know sigma, the population standard deviation, will insert more variability in what can happen. So your families have to be a little wider, so to speak, in order to gain the same degree of confidence. Does that make sense?
Yeah, thank you so much.
Mm-hmm. And the n could be different things. Could be 20, 30. You might want to play around a bit to kind of come up with different critical numbers. Just to make sure you can sort of reproduce the calculation. So I'd like to go back. Okay, good. So what I'd like to do is sort of go back and talk about an example that we talked about, I think, quite a lot, the coin flip example. I'd like to sort of do it sort of using these techniques. So you might remember we have a coin. We flip it 50 times. We get 30 heads. Can we say anything about P, if we let P denote the true probability of getting heads on a single flip? Now there are various things you could say. In the written assignment 4, you sort of went through an exercise where you tried to use Bayes' theorem to say something about what you feel like, whether or not the coin is fair. It's dependent on various assumptions that you might make. I don't want to do that example. What I want to be able to do maybe is to cook up a confidence interval, which may or may not include the true proportion. And so how would you actually cook up the confidence interval in this case? What sort of guarantees do you need in order to convince you that the sampling distribution for the proportion of heads makes sense? How can the problem be cast in a way that's similar enough to what we're talking about to make sense of it using these techniques? So for us, we might think of P as representing, this might be important for later, some long run probability. Now, a few people mentioned this when they were thinking about this problem. If you flip the coin, an infinite number of times, the proportion of heads is whatever P is. So that's sort of this frequent dispersion of probability. It's not, you're not sort of telling anyone exactly what P is. Other than that, it's sort of this long run probability. I mean, really long run, I guess, if you think about an infinite number of flips. So for our own sort of peace of mind, if we want to cast this problem as one where we're trying to estimate a proportion, we at least have to convince ourselves that the sampling distribution for such an experiment looks the right way. And so we have to think about the randomness principle. Randomness. Is that condition satisfied, if we flip the coin 50 times? This is difficult to say. And the reason is that you're not picking out 50 different flips from an infinite number of possible flips. You're flipping the coin 50 times in a row. So you're flipping coin 50 times in a row. And so, this randomness or the independence condition, I mean, maybe the 50 flips are in some way related. Maybe the wind conditions are such, which are causing the coin to do certain things. Or maybe the person doing the flipping is causing it to do certain things. But most people are going to wind up rejecting, are going to reject the idea that there's really anything special about the 50 flips, even though they're all in a row. And again, I mean, there's a difference between flipping a coin 50 times in a row and imagining like the universe of possible results when you flip a coin infinitely often, and choosing 50 random flips to kind of see what you get. Those are not the same. But if you flip a coin 50 times and you're not doing anything special, maybe it's close enough. So before I go on, do people kind of understand this distinction? If you have an infinite sequence, picking 50 things in a row is different than randomly picking 50 things out of the infinite sequence. But it's a distinction that most people feel will probably not make too much of a difference if you don't suspect that there's anything going on with the person flipping the coin 50 times in a row. So it's probably mostly okay. Again, if you get a weird result, maybe you feel like treating the analysis with some caution. I mean, another thing we can say is certainly 50 is much less than an arbitrarily large number. So again, you can kind of convince yourself that the so-called 10% condition is satisfied for our analysis. And finally, you can check pretty quickly, that 0.6 times 50 and 0.4 times 50 are both greater than 10. So 0.6 times 50 is, of course, 30, and 0.4 times 50 is 20. And so what the author calls the success failure condition is okay. The biggest problem, the biggest obstacle, I think, to treating this as I'm suggesting we treat it, is probably right here. And again, whether or not you might personally feel that there's a problem with treating 50 flips in a row as being, not that special, versus sort of randomly choosing 50 positions in an infinite sequence of flips. Again, opinions are going to vary about that, and it's okay that they do. But if you broadly accept that the techniques apply, then we'd expect to get a formula. So if we want, say, a 99% confidence interval, or a family of those in this case, we get a formula that looks like our estimate minus a margin of error, our estimate plus a margin of error. And since we're dealing with proportions, our margin of error should be equal to a critical number, which depends on the confidence level, multiplied by the value of the estimate, multiplied by the standard error, right? So this thing right here, in our case, what do we get? You get 0.6, 0.4 divided by 50 right here. And for the value of Z star, 99% confidence interval. It's embarrassing, I can't remember it, but you can just use the normal calculator to get it pretty quickly. So that's right here. And so, we play the same game. What should the critical number be? Put in, 0.99 right here. We get a critical number of about 2.57. And so we get a formula that looks about like this. And, you can figure out what, that is, because we know that, and we know that p hat is 0.6. So in this example, you can come up with a confidence interval that is in some way associated to the estimate that we have. And I'll go ahead and use Excel to do this pretty quickly, because it multiplies numbers pretty fast. So I'll just enter 0.6 here. That's the value of the estimate. For the estimate of the standard error, I want the square root 0.6 times 0.4 divided by 50. That's something on the order of about 0.069. Critical number is 2.57. And so if I wanted to calculate the margin, if I wanted to calculate the upper and lower confidence limits, manually, you'd enter 0.6 minus that times that. And so the lower confidence limit, something on the order of about 0.42. And the upper confidence limit you compute in the same way. You get 0.6 plus, again, standard error times the critical number, which of course is somehow going to correspond to the confidence level, and you get 0.77778. And so the upper and lower limit, the confidence interval that we get is fairly large. Maybe more importantly, it includes 0.5 within its bounds. So the lower limit's on the order of about 0.42, upper limit is on the order of about 0.77. That definitely includes 0.5. So if your instinct on this problem was to think that 60% heads or 30 out of 50 is not terribly unusual, that's also kind of what this confidence interval wants to confirm. So does this make sense? 0.5 is in there. 99% is a reasonable level of confidence in this case, I would say. And the reason is that, and I guess my reasoning, to use such a high level of confidence would be something like this. If you think about how coins are minted nowadays, there's a great degree of precision. I mean, they're manufactured, you would hope, in some kind of uniform way. They're not irregular. So, you would not need to think that, you wouldn't want to, reject the theory that, the coin was actually fair when it wasn't, even if you got an unusual result. You need strong evidence to do that. And that stronger evidence would somehow be associated to a higher confidence level, if that makes sense. If you choose lower confidence levels, the interval that you would get, or the family of intervals, would be uniformly more narrow. And so in those kinds of situations, you would wind up thinking that the coin wasn't fair probably far too often, given what we know about how coins are manufactured in the modern world. You would need fairly strong evidence, like something crazy would have to happen, like 45 heads out of 50 flips, to cause you to think that, there was something unusual, at least about the 50 times you flip the coin. So is everyone with me so far on this? So it's just an example. I'd like to treat that example in a way that we're going to treat it today. Discuss a little bit about, how we change our point of view, maybe going through, again, the steps of this type of example. So let me get to a new page. Today and this week, we're going to be talking about something called the Null. So we'll talk more about this example and, related to this in just a second. The Null hypothesis significance testing framework. I just don't want to write it down every time. So what does it mean? This framework that you're talking about is in some way equivalent to the idea of interval estimation, at least some version of it. And so a lot of the stuff that we do with interval estimation will seem familiar. The framework depends on a couple of things. One of those things is, as you might guess, the sampling distribution of the statistic. So you need to know about that. And so, there's always some verification that that the sampling distribution is normal, or you feel like the standardized means, in some general sense, are at least t-distributed. So you always have to go back and check, the three conditions, or at least find a reason to convince yourself that they're reasonable, at least in this example. And maybe the thing that's a little bit newer, we make some sort of assumption, or we generate a statistical hypothesis about, the nature of the object of study, like in our coin example. It's a good example to consider. So most people, when they're thinking about that coin example, so it's the second thing that I feel like I should talk about a little bit. When you think about what these two things together mean, 1 and 2 sort of imply that we're going to use a certain probability model to discuss the evidence that appears in an actual experiment. So you can think about this process as organizing evidence, or at least organizing a way of thinking about the evidence coming from an experiment by comparing the evidence to what you expect, what is expected in a mathematical model for the type of problem you're considering. And so, you know, what might that mean in the example of the coin? So when you're thinking about, you know, the mathematical model we're going to be using to evaluate the evidence is probably not that surprising. You know, if it's a sampling distribution, you're thinking that it's at least normal. You know, you feel like the central limit theorem applies in the cases we're going to consider. So, you know, either you're thinking about an actual normal distribution if you're dealing with proportions, or you're thinking about the t distribution if you're dealing with means, provided that you don't know the standard deviation of the population. So one of those two things is going to be you know, sort of central to the discussion. So back to the coin example, since it's a proportion, you know, we're going to likely be dealing with the sampling distribution being normal. And so in the example that you're considering, you know, in the future for future problems, you're always going to have to think a little bit about you're always going to have to think. Let's see, where am I at? Where are my notes? I lost where I was at. You're always going to have to think about these conditions. You know, the randomness condition, the 10% condition, the NP times P condition, the success value condition. So if you're dealing with proportions, these things always come into play. Why? Because they're sort of the minimal level of they're a minimal set of conditions which are needed in order to make the belief that the sampling distribution of the thing you're looking at, to make the belief that the sampling distribution of p hat is normal, a plausible belief. You know, if you have different failure points along the way, then, you know, you no longer can make that assumption. And at that point, lots of different things could be true. You know, if your sampling distribution has some weird features, then the techniques that we're using or we're trying to use to do the inference will break down in some way. So in the coin flip example, I won't recheck the conditions, but I'll just say always check the conditions. You know, do you think that the conditions hold? And, you know, in our example with the coin flip, it's plausible that they hold. The thing that's new is we have to formulate a statistical hypothesis about the coin. And in a way, a statistical hypothesis is in some sense a pair of beliefs, a null hypothesis and an alternative to which it is being compared. So when you talk about a null hypothesis, you typically write it in this way. So a null hypothesis is always a statement about the parameter. So if we're thinking about our coin flip example, you know, the most plausible scenario is that the coin is fair. That's a reasonable null hypothesis. So if the coin is fair, what we're saying basically is that the true proportion of heads should be 0.5 in the long run. That's a pretty reasonable belief about most coins. It seems to be borne out by a lot of experimental evidence. It's reasonable from the point of view, if you think about coin manufacture, we'll go with P equal to 0.5. The null hypothesis in most cases is the hypothesis that is uninteresting. Nothing is interesting with the null hypothesis. The surprising result would be to find out that something happened which caused our belief in that to change. And that's kind of what the alternative is. So the alternative hypothesis that we'll treat in this example is that is sort of everything else, that P is not 0.5, something other than 0.5. And so when you formulate the statistical hypothesis that you're dealing with, you have a null hypothesis, which is sort of the uninteresting hypothesis. And then you have the alternative, which is in some sense the other thing, everything else that could happen. Now, for what we're going to talk about, there are one-sided alternative hypotheses. There are two-sided hypotheses. What I want to say in the example we're looking at right now with the coin flip is that it is a two-sided hypothesis because something unusual could happen on both sides of 0.5, which would cause you to question the null hypothesis. You could get an unusually large or small number of heads in this case, and both would be interesting. So does this make sense so far? That's what's new about this week. It's the formulation of the null and the alternative, and sometimes this is a bit confusing. So does anyone have any questions? We haven't really done anything yet other than that, but that's actually quite a lot, I think. So is this okay so far? So good. Again, think it through, think about it. Back to the example. When we have these as the null and the alternative, And if we check the conditions, what we're really saying with these things combined in some sense is that the sampling distribution for the proportion of heads, which again I'll denote with this p hat symbol, is a normally distributed random, the p hat's a normally distributed random variable. Since I am assuming that p is equal to 0.5, I'm saying that the peak of this distribution is over 0.5. I'm saying that p hat is normally distributed with mean 0.5 and standard deviation 0.5 times 0.5. 0.5 is of course 1 minus 0.5 divided by 50. I'm thinking about 50 being the number of flips. So these two things together, the conditions that apply, the belief that the sampling distribution of p hat ought to be normal, and then look, we think that p ought to be 0.5 because it's most plausible. We're sort of assuming that this is the picture that we see. We see a nice normal distribution centered over 0.5 for p. This is the mathematical model that these two things, that the condition check and the null and alternative, the statistical hypothesis, generate. It's this model. And so what happens next is that we do the experiment and we get a realization of p hat. And if you go back and remember that problem from written assignment 4, the realization is 30 out of 50, it's 0.6. And we ask ourselves the question, is p hat equal to 0.6 consistent? Is it compatible with the model we're using? Now remember, that model you're talking about is this guy right here, right? This is the mathematical model we're thinking about being true for a coin. So is 0.6 compatible? Well, in a picture like this, you know, we're sort of seeing, you know, all possible p hats basically appearing here, and here's 0.6. So, you know, we kind of already suspect that it's actually quite compatible, but we have to ask, what does compatible mean? And for this, we have to kind of give a tolerance. How far away from 0.5 would we need to be surprised? And you know, in this situation, compatibility is judged. So it's funny, compatibility. I could always write these things on the board much more easily by looking at a couple things you can look at, but looking at a significance level associated to what we're doing. Now, for the problem we're working on, the significance level is associated to the total area in the tail. So let's go with, so significance level alpha, that's usually the notation that gets used for it. Let the significance level be 0.01. So 0.01 means that with the model we're using, so remember it's centered over 0.5, 0.01 establishes regions of, it establishes the location of extreme regions. So basically, if the significance level is 0.01, then there are two numbers, one here and one here. And what you're saying, and these numbers are symmetric with respect to 0.5. There's the same the same distance from 0.5 on the right and the left. Now, so in a case like this, significance level of 0.01, what we're saying is that that region right there has area half of 0.01. That region right there has area other half of 0.01. So 0.01 is the total area in the tail regions of the distribution. So before I go on, and I guess what we're saying is, if this is the model, And if we get a result either over here or over here, what we would be inclined to say is that the experimental result is not consistent with the mathematical model that we are using to analyze the evidence. Does this make sense so far? The significance level dictates where those regions actually are in this type of work. Is this okay so far? Okay. Remember, you'll have to do this in just a second. So it's worthwhile. If you have any questions, just stop me along the way. So how do you find these regions? How do you find the region? How do you find the tail area? So go to StatCrunch, and we're using the normal calculator with mean mu equal to 0.5 and standard deviation for the sampling distribution. So I should write maybe p hat down here, equal to the square root of 0.5 times 0.5 divided by 50. Now that's, if I remember, I did that calculation earlier today before I came here. I think that's about 0.0707, but you can check that. And so in order to find out, where the cutoffs actually are, the range, if we wanted to find that sort of region of extremity, you go to StatCrunch, go to Stats, go to the normal calculator. So go ahead and use between in order to find it. The mean that we're using here is 0.5. The standard deviation is 0.0707, I believe. You might want to check that. And if my alpha level is 99%, if it's 0.99, I would enter 0.99 right here. Or rather, if my alpha level is 0.01, then the central region has 99% of the area if the tail regions are to have 1% of the area. And so you do something like this, and you wind up finding cutoffs which extend between 0.31 and 0.68 for this model. So I can write that down if I remember what the numbers are anyway. 0.3179, 0.6821. I hope I can remember that. Yes, Lily.
So if you're looking at the tails and you're trying to find like 0.1, you're looking for 0.1 on each tail, or you're looking at 0.01 total?
0.01 total, it's 0.005 in each tail. If you're dealing with a two-sided test, surprising things could happen in one or the other tail. So you're thinking that the mathematical model is incompatible with the evidence if you get either way, if that makes sense. So for a level, again, it depends on the formulation of the hypothesis. But in this case, what we're thinking about with the way the alternative is phrased, we're surprised either way. So basically, we get something in one tail or the other tail, and we would be inclined to declare the mathematical model and the actual empirical evidence not reconcilable. Does that make sense? You could formulate them differently. We'll see this in just a second. But it's 0.01 in the tails combined, the way we're looking at it right now. Is that good?
Yes, sorry, I put my hand down.
Wait, is your hand still raised?
Oh, no. Well, it was, but I put it down.
Oh, okay. All right. So, I guess in the picture, I needed to really write those down pretty quickly because I was forgetting, where the cutoffs were. So you see that you have, it's not a great picture, but I hope it captures the idea. You have that tail area, you have the center over 0.5. And so if we got any empirical evidence that fell within this region, we're not surprised. We're not willing to declare the mathematical model to be incompatible with the experimental result. But if we get anything in this range of results, like here or here, anything in that range to the right of, I think it's 0.6821, and to the left of 0.3179, anything in that range would cause us to think that the mathematical model at a significance level of 0.01 is not, it's not compatible with the evidence at the significance level of 0.01. Now, if that happens, if we got p hat bigger than 0.6821, or we got p hat less than or equal to 0.3179, the way that you would formally reject it, the way that you would formally write it is that you would reject the null hypothesis at 0.01 level of significance. But we don't. We get p hat, we get its realization to be 0.6. It's toward the right of 0.5. Maybe that's not so surprising. But the fact that it's to the right, so which is not extreme enough. So we fail to reject the null hypothesis at a level of significance equal to 0.01. So these types of formulations wind up being very important. When you're thinking about a test of significance, which is what that just was, you will either reject the null hypothesis under the condition that the empirical evidence is too extreme relative to the mathematical model that you're considering, or you will fail to reject it. A few words of caution. When people were sort of thinking about this environment, this null hypothesis significance testing environment, it's this 100-year-old creature. The sort of philosophy behind this is that you could never, they were trying to get around, I guess, the so-called problem of induction, right? And philosophically, the idea was that you could never prove something necessarily. Everything was always tentative, but you could reject things. And so when you see something like this, if you fail to reject, that does not mean prove the null. You'll never prove a null hypothesis, never. You will reject it sometimes in favor of the alternative, in which case you have a result which is called statistically significant. But you will never prove the null. It's sort of it's a creature that these words are sort of a creature of the type of philosophy which lies behind these sort of testing mechanisms. That you'll never truly prove something. The conclusions are always tentative, but you can certainly reject things. So when you're thinking about writing things down or writing up your results, the author of the text takes you through sort of a step-by-step process. It looks a bit like this, or at least a version of this. Does anyone have any questions so far? Is this okay? And so there's another potential approach, and I'd like to mention it as well. Right now, I feel like I've talked a lot today. Sorry about that. You'll get a chance, I think, over the next couple of classes to do some things. You can also consider this problem. Turns out you can also measure the following probability. The probability of a realization, again, I want to just return to the coined example of a realization of p hat at least as extreme as 0.6 if h naught is true. And so if you're trying to measure that probability, this probability is known as a p-value. And sometimes a p-value, another name for it, is the observed level of significance. This is worked out in a way similar to what you get with the significance level. So how do you do that? In a case like we're considering with a two-sided test, if our null hypothesis is that p is equal to 0.5, and if the alternative is everything else, p is something other than 0.5, we're tending to think that extreme events occur on either side of 0.5. So extreme realizations for us, if that's 0.6, will either occur over here or they will occur over here. So either to the right of 0.6 or to the left of 0.4. What does 0.4 and 0.6 have in common? They're equidistant from 0.5 by some units, by some standard deviation measurement. So if you're thinking about calculating a p-value, extreme for us, and extreme, a result at least as extreme as 0.6 can occur either in the right or the left tail under this formulation. And so the p-value that you would get, so let me again go back to StatCrunch to compute it. If you're trying to compute the p-value in that case, what would you really be looking at? What's in the tails, right? So you add up the area in the tail, so you fix this number to be 0.4, that's the left cutoff. You fix the right number to be 0.6, that's the right. The mean and the standard deviation, I'm assuming, in the model. So when I hit compute, the central area has the central region that you see in front of you, the red region, has area 0.842, which means that the tail area is everything else. So you would say that the p-value is about 1 minus 0.842 from quick calculations, it's 0.158. 0.158 is bigger than 0.01 by a lot, so you fail to reject. So when the p-value, when the observed level of significance is larger than the level of significance, you fail to reject. What you're saying with this is that if, or under the null hypothesis, the thing that you're seeing happen is not extreme enough. So larger p-values tend to be associated with a series of events with an experimental result, which is not too surprising, or at least is not in a surprising range of results. And so when you see a large p-value like 0.158, you will tend to fail to reject the null. Low p-values tend to be associated with the rejection of the null. So notice that when we're doing these things, when we're thinking about either looking at regions of rejection versus non-rejection, or when we're simply thinking about p-values, in both of those cases, we kind of get consistent results. The results are kind of also consistent with the creation of a two-sided confidence interval, but I probably don't want to talk about that right now. So before I move on, does anyone have any questions about this? So again, fail to reject, p-value too large. It's similar, you don't have to do things more than once. You can either cordon off a region of rejection and think about the problem from that point of view. You can calculate a p-value. If it's too big, then you fail to reject. And that's kind of where we're at right now. I guess what I would like people to do, so let me bring up, like in the last few minutes of the class, there was this thing we started to work on. And I'd like to see what the groups can do with it. So there's a handout under classroom materials, and I'd like to turn the groups loose on it for a few minutes, then we'll come back and discuss it. Think about what it means in relation to the type of examples we're doing right now. It's just problem 1. So it's this one right here. It's the long jump problem. We talked a little about it last week, but from a different point of view. I think you might remember last week we calculated a confidence interval associated with this particular problem, 99% confidence interval. What I'd like people to do in this case is to attempt the problem. It's not quite what we did because you're not thinking about proportions, you're thinking about means. But I'd like the groups to try it anyway. So the problems that I'd like people to consider, what do you think the statistical hypothesis actually is? On B, it's a lot like what we did last week. Do you think that X bar is normally distributed with mean mu and the standard? Do you think X bar is normal, right? So what kind of conditions where you need to check? And then as a group, I'd like to maybe think about the rest of it. But this is under the this is under the classroom handouts for this week. So that's kind of where we're at right now. So I'll break people into groups for a few minutes, maybe not that long. Just consider the first couple of questions, A and B. Try to formulate the statistical hypothesis. Try to think about what conditions you'd need to obtain in order for X bar sampling distribution, in order to convince yourself that X bar sampling distribution is normal. It's about 155. I'd like to meet again in about 8 minutes at about 2:03, and then talk a little about the differences between this problem and the problem we've done that we did as an example. So you should have your group invitation. So let's meet again at about 2:03. All right. So people are returning. Did the groups have questions? I hope the groups had questions.
Can we just go through it?
Yeah, there are at least, yeah. I mean, there are at least two things different about this problem than the one we already did. And one of those is that you're not talking about P, but you're talking about mu. And the other issue is that it's a one-sided test rather than two. So let's sort of talk about the differences between this example and the one that we did. So when you're looking at this type of example, you have this business about, you have a long jumper helping to prove the distance. Let's see. Okay. And, so you have some new training conditioning, some new training regime. Before the training regime was enacted, long jumper is going at about 24.5 feet per jump on average. After the new routine, you take the series of the first 32 jumps after the routine, you get something like 25.1 feet with a standard deviation of 1.26. So that 1.26, you're given an estimate for X bar basically and S. So does the new sample give evidence that this person has increased the average jumping distance? Now, there are several problems with this, with using the techniques that we're talking about. We'll get to those in just a second. But when you're thinking about the hypothesis, maybe the problems don't appear there at least. So the null hypothesis and the alternative, these are always statements. These are always statements about the parameter. So in this case, the null hypothesis is that nothing has changed. Things are the same before and after. And the idea there is that you'd need evidence that was presented, which would, in order to disconfirm that belief, you would need some evidence that was reasonably strong to convince yourself that that was not right. Now, when you're thinking about the alternative hypothesis, I would say that in this problem, it's not a two-sided test. You're looking at one rather than the other tail, and the reason is the way that the problem is formulated increased the average jumping distance. So when you think about mu as representing, I should probably write this down as well. If the symbol mu represents the average jumping distance, the way we're thinking about the problem is that either nothing's changed and what you're seeing in the 32 is just associated to sampling variability, or something has changed. Now, in this case, mu being greater than 24.5, if you get a value of mu which is considerably larger than 24.5, you would tend to reject the null in favor of the alternative if the methods apply. So what I would say is that this is different. Notice that this inequality is not just an inequality not equal to. And so this is probably how I would formulate it. Do you have any questions about that so far? So it's one-sided. You want to know about one tail. Yes, Lily?
Why would you not say if mu is smaller than 24.5? Why would you not go the other way?
In this case, so you're saying that why don't you have a statistical hypothesis that looks like this? Oops, you mean this, yes?
Yeah.
So the reason that I would say it was this versus this is because you're interested in whether or not there has been a right-sided increase, right? Whether or not there's been an increase. And so when you're rejecting the no change hypothesis, you're doing so in favor of the belief that mu is greater than 24.5. That's what's, so basically if you reject this, you're looking at an alternative that there has been an increase. So you're kind of saying that there's evidence in favor of an increase. And so that's kind of trying to answer this question. that you've actually increased the jumping distance. I guess that's what I would say. But if you reject this null hypothesis, then your alternative is that the person is worse off, right?
Yeah, that makes sense.
So that's why it's so when you're thinking about formulating, so that's why I would not say that. When you're thinking about formulating a statistical hypothesis, the critical thing to do is to analyze whether or not you think, like in the first example, we're dealing with the coin. You know, you can formulate that as a one-sided test as well, but I think a one-sided test in this example, in particular, a one-sided test in this direction makes sense because of the way the question's phrased. And so, I mean, I guess, another thing to point out is that if you were interested in this hypothesis, you're just trying to think about whether or not the person is worse off. I think that an average of 25.1 you'd probably not reject the null in that case, right? You wouldn't have evidence that the person's worse off if the average was better. So really, I think this is probably the way to think about the problem in this case. But when you're thinking about, you know, which side or whether or not it's a one or a two-sided test, a lot of this is context dependent. You have to read the question very carefully. Think about what alternative might make sense given the context of the question. The concern I would have about the techniques, I'd say that the randomness, I don't think that's a great spelling, randomness. I think there's an issue here. So my own opinion about it is that if you think about what's being said, you're imagining this person is having, you know, these many jumps over a lifetime of long jumping. And you're taking maybe the first 32 jumps after the training regime has changed. Do you think that those 32 jumps are randomly selected out of some large population of jumps after the new training regime has changed? I don't know that that's that believable, right? Like maybe there's some initial change, or maybe, you know, you see some variability just because it's a new training regime. It's got nothing to do with the content of the regime. Could be lots of reasons to suspect this is an issue. So beware, you know, think it through, kind of use, sort of use your common sense when you're thinking about the problem. In other cases, you know, it's not clear that this is really satisfied in this example. In other cases, it's probably more clear, like if someone comes around and says something like, we conducted a survey and we gathered a random sample of a certain size, you can probably convince yourself that the randomness condition is satisfied. You also wonder a little about the 10% condition. You know, do you think that 32, you know, even if they're not randomly chosen, do you think that the 32 jumps, you know, are less than 10% of the population of all jumps that this person could have taken? I mean, again, there's a question here, I guess is what I'm trying to say. You know, but at least 32 is big. So when you're thinking about the central limit theorem, the conditions for inference, I've got some doubts about the randomness condition, about the 10% condition, but at least 32 is large. So right now I think it's about 211. So I'm not going to take up any more time. I think we'll probably begin with this example on Wednesday. So try to remember where we're at. I'll go ahead and keep a record of it myself. I'll probably go through it maybe and then let you try a few more problems when you're thinking about a one-sided test. But for today, I think that's enough. So I'll stop recording now, time, and then we'll continue on Wednesday.